Hello everyone and welcome to our presentation, an aperiodic prescribed performance control scheme for uncertain nonlinear systems. My name is Alexandros Nikou, I'm from Ericsson Research, and this work is in collaboration with Christos Verginis from Uppsala University and Shahab Heshmati from Aalborg University. To start with, it is known that in many engineering applications we have models that are uncertain and they are nonlinear. So the challenging part of this system is to address uncertainty in order to control them to perform automation tasks. There is a vast majority of feedback control laws in the literature, and out of these approaches, a promising category are the ones that are model-free controllers that can guarantee predefined transient and steady-state performance without a need to know any model of the system a priori. At the same time, prescribed performance control have been addressed in the literature usually with periodic sampling. But if we think from a resource allocation perspective, periodic sampling sometimes is not preferable because we might need to unnecessarily trigger the actuation of the system when it's not required. So motivated by the above mentioned things, in this work we address the problem of event-triggered prescribed performance control in a combination of model-free controllers and event-based ideas, with a novel triggering conditions as we will see later. So the contribution of this paper is we propose a novel feedback control law that exhibits the following attributes. It is updated aperiodically, as we said, only when it's necessary under a novel event-triggered condition. We will see that condition. It is bounded by a predefined upper bound that is known, and this depends on the parameters of the system and the design parameters of the controller, and it can guarantee stabilization to a desired state within a predefined time, which is useful for scheduling and constraint control in the time applications. And it is also robust to external disturbances, uncertainties, and modeling inaccuracies of the dynamic model. Also, it has low complexity since it's given in a closed form, so it can be directly implemented in the real-time platforms. Now, we have two background slides for this to understand this contribution. So first of all, the event trigger control for linear systems. It is the idea started from this famous paper in 2006. So by given a linear system with x dot equals ax plus bu for a sequence of execution times tau 1, tau 2, tau 3, the control input signal is the control input is kept between two different execution times. The control input is k times x, and it's kept constant. Then we have the error. The error is always the last triggering time minus the current state. So then we have this. This is a representation of it, and then we have the famous theorem that says that there exists actually bound that between these two triggering times, if someone uses this triggering mechanism, the norm of E equals to sigma. That sigma can be designed and it's positive times the norm of the state, then it can guarantee an event trigger configuration for the system. So the control input, as we can see, between two triggering times, it's kept constant, and this can lead to nice properties and actuation capabilities for the system. The second ingredient for this presentation is the prescribed performance control, which started from this famous paper. So the idea is that we would like to keep the error of the dynamics, even it's a stabilization task or trajectory tracking or others, we can define an error, and we want this error to be kept between two performance functions. So the performance functions are decay functions that usually are given as this form. So we have the rho 0 starting here, rho infinity, and then we can have an exponent how steep we want this convergence to be. We can be a bit more relaxed or very steep, and also we can also predefine how open or closed this funnel we can be. So we can define both transient performance and steady state. This can be given by performance function. So there is a methodology that under specific assumptions one can design feedback control laws that guarantee this property. So in this paper, we would like to combine these things, the prescribed performance control and the event trigger control strategies, which are two powerful techniques in order to have in order our controller to have the attributes we just mentioned. So we start with the dynamics of the system, we give the assumptions that are required, and we show the results. So we start with a nonlinear system in continuous time and at certain dynamics. So x denotes the state. This is the dynamics, x dot fx omega plus g times u. U is the control input, affine. Then we have that these two vector fields are unknown, so we don't know their structure. We assume that, and also we say that omega models this term here. It's a vector that models the external disturbances, uncertainties, and model mismatches, and it's also assumed to be unknown. We do two technical assumptions in order for the proposed controller to be well defined. So we say that the functions f, g is the functions that we saw from the dynamics are local ellipses continuous, and also there exists a positive constant f, which the infinite norm of f is upper bounded by this f for every x omega in R. And also we say that the function g is strictly diagonal dominant, with all its diagonal entries strictly positive. So this means that GII is the symmetrical elements of the vector field G, and then is the summation over the rest. We want these differences to be lower bounded by a positive contact. We will see that this lower bound also is important for the trigger condition. Then the task that we consider here is navigation. So we start the states from initial configuration, and we want to steer the system into a desired configuration. So naturally, we define an error term for each of the component of the vector x. I, for notation here, we will always have the element of the vector x, and k will be always the triggering condition. So the triggering time that the triggering happens. Then the performance functions are given by this term. As we said, it's like the funnel starting from rho 0, rho infinity, L for the transient performance, and rho infinity for the how close or open we want to be the funnel in the steady state. Then we define the normalized errors. So we define these errors xi as the inverse matrix of rho times e. So the normalized errors, if these errors are between -1 and 1, then our signal is always inside the funnel. So we want always this normalized error to be between -1 and 1 in order to guarantee the prescribed performance. And then we define a sequence of sampling times, Tik, which are aperiodic, of course. We are dealing with aperiodic control laws. And then the goal is to design an aperiodic feedback control law such that the error remains between these two performance functions. So the error always stays inside these performance functions. So the main result for this paper is the main theorem that we prove in the paper. So by choosing a parameter kappa, which is larger than this term has the L and rho are the parameters of the performance functions. Mu, we will see that is a parameter also, then F bar is and G underline is the dynamics, the bounds of the dynamics. Then the proposed feedback control law is equal to minus kappa times xi. Xi, recall, is the normalized error. Tik is the k sampling time for I component vector in vector x. So the triggering mechanism is that we trigger when xi is becoming mu or minus mu. So actually, as the signal evolves, we are triggering exactly when the signal is about to go outside the funnel. So we choose these parameters as we want. So the closest this parameter is closer to 1, then it's closer, the closed loop trajectories are closer to the final. So by this technique, in these parameters design, we guarantee the prescribed and transient state performance of the system, the zero behavior is excluded, all closed loop signals remain bounded, and the system is driven from initial configuration 0 to desired at a precise time t. So an intuitive example for it, for the previous theorem, imagine that we are in R2, we have the normalized errors x1 and x2 that are evolving over time. We can see that mu is a design parameter, and we know that when x becomes 1 or -1, then the system goes to instability because it approaches the funnel. So we would like mu to be a parameter less than 1, and we trigger when the system goes to 1 or -1. This is the idea. And we know that this can guarantee stability because as long as the trajectories remain inside this funnel, then all the conditions are satisfied and we have prescribed performance. So a small proof sketch. So we can see that xi, we will prove actually that xi remains bounded from minus mu to mu, which means that the infinite norm of u is bounded by kappa times mu. So this is a bound of the controller. We know it a priori and depends with the dynamic bounds and how steep we want the funnel to be. The proof is separated into two cases when the xi, the normalized error, becomes mu or minus mu. Recall that I is the element I of the vector x and k is the sampling time, triggering time. So by differentiation in the dynamics, we end up in this formula where capital lambda I is a summation over the non-diagonal elements of matrix G times the corresponding control inputs. We prove that this is lower bounded by upper bounded, by kappa times underline G times mu. Underline G is the lower bound of the matrix G. And then after some manipulation, we prove that the limit of xi dot when the triggering time is negative and the derivative of xi is negative along all the interval. This can guarantee that xi is always remain between minus mu and it triggers when it goes close to mu and close to minus mu. This is the idea. And we can show a simulation for it. We consider a nonlinear system in the R2. This is the structure of the system. And then we have, we start from x0 and we want to go to x desired. This is the f bar is the upper bound of dynamics, g underline is the lower bound of matrix G, and we want this stabilization to be performed in 3.5 seconds. So we can choose appropriate the parameters of the predefined conditions and the exponents. So we can choose exactly the funnels to be as tight as we want, and we want to make them even more tighter in the time that we want the stabilization task, so at 3.5. So by applying the suggested control law, we can see that the error signals remain always inside the funnel and they are triggered. So the triggering time happens only when the closed loop trajectories are about to go to instability. Recall that when the closed loop error signal goes close to the funnel, then the system has to stay inside there because otherwise it will be unstable. So we guarantee that with this parameter mu, so actually the parameter mu shrinks a bit the funnel, and then we guarantee that this system will always remain within that bounds. And then we can see the normalized errors always from minus mu to mu. Mu is chosen to 0.7, and we can see the triggering times. And we can see the control input also upper bounded by minus 1.5 and 1.5. Recall that the upper bound of u was k times mu. We see that it's kept constant between two triggering times, and this was the end of our presentation. So we can conclude we have proposed a novel event-triggered mechanism for prescribed performance control under the given assumptions, and the low complexity strategy can guarantee stabilization in predefined time, and future directions will be devoted towards enlarging the category of class of systems. We want to be this to be applied in. We have some ideas how to do that to be in a larger category of systems, and also we would like to perform this in a data-driven approach. Thank you very much for listening.